Hi, this talk is about modern technologies applied to experimental analysis of the physics of a simple toy. Physics toys have been used traditionally in physics education, mainly for demonstrations as a way to engage and to show that physics is everywhere in simple but interesting objects. Some toys are challenging to analyze from a theoretical perspective and even to analyze experimentally. The yo-yo is an ancient toy rediscovered in different times and places and popularized early in the 20th century. It's made up of two discs joined by an axle and a string that is wound around the axle. The player then holds one end of the string with his or her hand, then lets the toy to fall, spinning and unwinding the string. At the lowest position, the yo-yo bounces back and starts climbing as the string is wound again in the axle. Here we have the free body diagram of a yo-yo of mass m and moment of inertia I relative to its axis, hanging from an ideal string and moving just in the vertical direction. Here are only two forces: the weight mg applied to the center of the yo-yo and the tension of the string applied at a distance r that is equal to the radius of the axle. We take in downward direction as positive and counterclockwise rotations as positive. Here we have Newton's equations, where a is the acceleration of the center of mass of the yo-yo and alpha is the angular acceleration of the yo-yo. The positive sign here corresponds to the yo-yo hanging on the left side of the string, as in the picture. So the negative sign corresponds to the yo-yo hanging at the right side of the string. The third equation corresponds to the relation between acceleration and angular acceleration for the non-slipping condition between the string and the axle. From these equations, it's easy to obtain the angular acceleration of the yo-yo that is constant as absolute value, but changing their sign according to the position of the yo-yo relative to the string. When the yo-yo is falling or climbing at the left side of the string, the acceleration is constant and positive. But when the yo-yo is falling or climbing at the right side of the string, the acceleration is constant but negative. So here we have the angular velocity at different phases of the movement of the yo-yo as expected from the last equation. In the first phase, the yo-yo falls along the right side of the string, then the angular acceleration is negative. The absolute value of the angular velocity increases. At the lowest point, the yo-yo reaches the end of the string, like a physical pendulum rotates around the end of the string, then the angular acceleration changes its sign, but the angular velocity is conserved as a consequence of the conservation of angular momentum. In the second phase, here, the yo-yo starts climbing, but now along the opposite side of the string, so decreasing its angular velocity until reaching the hand of the player. At this point, The yo-yo falls again in phase 3 with the same angular acceleration, positive, increasing the angular velocity until the lowest point again. So, despite its simplicity, the experimental analysis of this kind of toys is not so easy to perform. A nice tool that we have in our pockets is a smartphone that has many sensors that turns it in a portable science laboratory. One of these sensors, the gyroscope, that measures angular velocity, is ideal for many experiments involving rotational dynamics, as is the case of the yo-yo. Here we have the experimental setup. For this purpose, we built a homemade yo-yo with two circular plates of methacrylate joined by an empty PVC pipe where a string is wound. The measuring instrument is the gyroscope of a Samsung S8 Plus, and the app chosen to read the values of the sensor is the Physics Toolbox. Then we start the experiment, turning on the recording function of the app and releasing the yo-yo after some bounces. The smartphone is stopped, and the experimental data stored in the phone is exported as a CSV file to a computer to be analyzed. So here we have the temporal evolution of the angular velocity of the yo-yo, and it looks similar to the previous theoretical analysis, but the plot shows several plateaus due to the saturation of the sensor when the angular velocity reaches 20 radians per second, here and here. We must mention that this value of saturation depends on the specific hardware of the smartphone. In the lower panel, two temporal windows are zoomed in. In the first window, the yo-yo travels up and down, up and down, up until zero angular velocity, and down until maximum angular velocity. Then the angular acceleration is positive. In the second window, the yo-yo travels up and down again, but now at the right side of the string, so the angular acceleration is negative. Performing a linear fit, the angular acceleration of both windows is obtained with almost the same absolute value, 65 radians per second squared. We also performed a video analysis that is useful tool to compare the experimental results obtained from the rotation sensor. The analysis is made from several frames here, measuring the angle frame by frame. So with these angles, a quadratic fit is performed to obtain the angular acceleration that is twice the value of the concavity of the barbell. So we have here an acceleration of 64.5 radians per second squared. This value agrees very well with the previously obtained value from the smartphone sensor. In conclusion, we have shown that modern devices like smartphone sensors are powerful tools to analyze the physics of simple devices like toys, that they are valuable tools to promote students' engagement and critical thinking. And finally, there are several aspects of this experiment that are worth discussing in classroom activities like mechanical energy, angular momentum, and many others. So thank you very much for your attention. We invite you to visit our website where we have many links to experiments and many papers about physics with smartphones and other devices. Thank you very much again. Have a nice day.